Okay. Good. So next, I will share the screen. Okay. And now we menu. Why this fucking thing? Let me go directly to Acrobat. That's it. And that's it. So can you see the lectures? Can you see the PDF? I don't know where it's at. Okay, thank you. So, well, just to say welcome everybody. This has been almost death by success because I wasn't counting so many people attending. So thank you very much for the attendees, and thank you very much for those giving the lectures, Meijian, Fabio, Tolga, and Guillaume. And let's start. So the plan is to have recordings of everything, and also to have in case there are presentations, to have them on the Indico. Yeah. And besides, some of the lectures will be on the screen, so on the computer. Some of them, they will be on the Blackboard. We hope that everything works okay. Okay, if there is any problem, please tell as soon as possible. Okay, thank you. Please begin. Go ahead.
Hi, so I will present today and tomorrow some introduction about Light-Cone quantization and Light-Cone perturbation theory. So as an introduction for this week, and then the other we'll talk about applications. So actually, so just a few words. So here, usually we are used to study quantum field theory using time or time-like direction to describe the dynamics, but here instead we will use an alternative approach, which will be to describe the dynamics of a system along a light-like instead of time-like direction. So that's an alternative formulation of quantum field theory, which in principle should be equivalent, but it's not that obvious. And actually, the two look quite different. So some things might be much simpler in one of the two possibilities, and some others might be more complicated. So it really depends on the thing you want to do and on the applications. And okay, this week you will see some applications in which it's actually quite convenient to use Light-Cone quantization, or equivalently light front, or also people call us that front form of relativistic dynamics. Yeah, so first, today I will focus mostly on scalar field case. So to discuss this Light-Cone quantization of scalar theory. And then tomorrow I will slowly move to describe the basics of QCD and QED in Light-Cone quantization. So first, I will do some reminders about Poincare invariance and covariance and so on, because I will need that quite a lot. So yeah, so first, okay, if we want to use light front, so let's first introduce okay, so here, yeah, I use this metric with the usual
It takes a while.
Okay.
Yeah. So just counter.
So I use a standard signature for the metric in particle physics. Just I recall that if you do a change of coordinates, you have the metric which would change according to the standard rules for tensors here. But okay, now, okay, so that was the metric in usual Cartesian coordinates with time and 3 space directions here. And now instead I want to use the Light-Cone coordinates that I define in such a way with the square root of 2 here, which is to avoid any Jacobian in the change of variable. So now I have x plus and the x minus coordinate, and then the standard x1 and x2 transverse directions. So now in this coordinate, the metric is looks this way. With if we write first x plus and x minus last. Okay, one thing to remember, because I will use it all the time, is that when we lower and raise and lower indices, yes, so that the upper plus is the same as the lower minus, and the upper minus is the same as the lower plus here. Whereas for the transverse, as usual, we just flip sign when we lower or raise index. Yes. So ij will be always my notation for the indices in the transverse plane. Okay. So so now let's recall a bit Poincare transformation. So first, Lorentz transformation. So here, transformation part of the Lorentz group will be a coordinate transformation, which transforms the coordinate as follows, with just a matrix multiplication, and in such a way that the metric is preserved. So yeah, so there are a few of such transformations. So for example, we have a very simple one, which is just rotations in the transverse plane. So like around the longitudinal axis. So this is just like standard rotation matrix in this like this, so this block here, where the plus and minus direction are unchanged. But there are more interesting ones. So for example, we have also Lorentz boosts. So if you consider a Lorentz boost along the longitudinal direction, so along x3, if you write it in Cartesian coordinate, you have like the plus, the x0 and x3 coordinate which mix with such pattern here. But now, if you write it in Light-Cone coordinate with plus, minus, and the two transverse direction, instead you have this. So now it becomes diagonal. So that's one of the reasons to use Light-Cone coordinate, is to make such longitudinal Lorentz boost simpler. Okay, so these were two basic examples. Also, I will focus on Lorentz transformations, which are, I will not talk about parity and time reversal and so on. I will just focus on the Lorentz transformation, which are connected to other identities. So then I can write and consider infinitesimal transformations, which are just a correction compared to the metric here. So in that case, the inverse is just like the split sign of the correction. And if you plug this relation here into the basically definition of the Lorentz transformation here, you see that necessarily this correction, this small correction here should be anti-symmetric. So yeah, so basically this tells us that we have that Lorentz transformations are like as an algebra which correspond to anti-symmetric matrices, like 4x4. So this is a dimension 6. So basically there is, I think that there is 6 generators for Lorentz transformations. So in terms of Cartesian coordinates, that could correspond to three rotations, so along the around the 3 space axis, and 3 Lorentz transformations along the 3 space direction again. But okay, of course, that will look a bit the same, a bit different if you think in terms of Light-Cone coordinates. Okay, and in addition, if we want to study not only the Lorentz group but also the Poincare group or algebra, we have to add as well the translations. So, okay, we just transformation, which are just translating the coordinates here, so it's very simple. Okay, so far I was talking about transformation of the coordinates. So just change of like change of the descriptions of the in that sense. So it's what is called passive transformations. But now I want instead to consider point-guide transformations, which will be acting on the system, like really moving or boosting or rotating the system we study. So if we and staying in the same coordinate system. So okay, so now if we consider a scalar field, and so scalar field, okay, which depend on the coordinate x. Now, if you perform such an active Lorentz transformation, it means that okay, you move basically your scalar field to somewhere else. So now, okay, it will have the so now the scalar field at some point x will have the value that it had before the transformation, but at the coordinate that that will become the transformation you look at now. So basically, okay, yeah, that's why it will depend in such a way that okay, so the transform field at x will depend on okay, will be the untransformed field, but at the point lambda1 x, which is basically the coordinate which will become x if you perform this Lorentz transformation. Okay, so and then if you consider instead a vector or a tensor field, there is still the same coordinate dependence, but in addition, you have to, like if you perform a Lorentz transformation, active Lorentz transformation, you have also to transform each index by just multiplying by the Lorentz matrix here, corresponding to that transformation that you want to do. Yes. Concerning the action of active translation instead of Lorentz transformation. Now, okay, we just have the similar story for the coordinate. Okay, which and so that's it. Okay, we just have to shift the coordinate x here, and in the opposite direction as what we had here. So that corresponds to that's another to having the lambda -1. So that is how you perform active point-guide transformation, so translation or Lorentz transformation on a generic field. So yeah, so transform the coordinate in such a way, and then okay, in the case of Lorentz transformation, also rotate for each Lorentz index. So now, if we consider infinitesimal transformation. Okay, what is the difference between the transformed and the okay, between the field before and after the transformation? So in the case of a translation here, so that's just the difference between the field that's field that's coordinate x plus a and the field that coordinate x. So if the translation is infinitesimal, meaning small a, we can just Taylor expand, and that's okay. So that's what we have here to at linear order in A. So if we do the same for the infinitesimal Lorentz transformation acting on a scalar. So now we have something similar with here, yes, and now if we consider the lambda to be infinitesimal here. So so if we expand here, we will get actually, okay, we arrive at such an expression here. So to linear accuracy in this lambda, so which is the difference between this Lorentz transformation we are considering and the identity. And at this stage, we can remember that this lambda mu has actually to be anti-symmetric. So if we, okay, for example, lower here the new index, and then using anti-symmetry of this, we can just rewrite this in such a way. So, okay, so you see that here for scalar field, when you perform infinitesimal transformation, okay, so that's how what you get here. With this funny combination of coordinate and derivative acting on the scalar field. If you have something which is not a scalar field, but for example a vector, then you still have such an effect coming again from the transformation of the coordinate that the field depend on. But you get extra contribution also because you rotate the vector field here. So when you Taylor expand here at small deviation of the for small Lorentz transformation, you get such an extra term here, and you again using the anti-symmetry you can rewrite in a similar form like this, but with some extra term. And okay, so this is what we can get here. So the interpretation is okay. So this is something that is a kind of generalized, I mean, somehow analog to orbital effect, let's say, and this one kind of spin effect. But okay, so this is not for just space, but for a full Lorentz transformation. So it's in a generalized sense. But okay, that's the idea. And so so here, if you have a more general tensor, you would have such a term acting on each like one term like this for each tensor index you add in your field. Okay, so such a way, for example, if you transform around two tensor, okay, you have the same matrix here, so this guy here, acting on each of the so here you have rho sigma. So here you act on the first index here, and here you act on the second indexes. And actually, okay, if we do one step back, it's we can find that so this was done for infinitesimal transformation, but actually now if you consider finite Lorentz transformation, actually there is a full parametrization of it, of the transformation using the things we have introduced. So the lambda mu, which is anti-symmetric and was assumed to be small so far, and then this kind of object here. Now, if we build this exponential of this, so this is the exponential of matrix basically. So here we have the mu and indices which are constructed, but then there are like still this rho and sigma indices. So in that sense, with respect to this rho and sigma indices, that's exponential of matrix. And so this object for generic lambda mu, not small anymore, then that would give you a Lorentz transformation. So basically, if you plug this expression for arbitrary rho into yes, into this expression, okay, that you will satisfy with this. So that means that it is a Lorentz transformation. And since it's parameterized by the lambda mu, and there are like 6 of them, so it means that here you fully parameterize the Lorentz group. Okay, up to parity and time reversal, but okay. So okay, So we understand how to play with Lorentz transformation on a vector and tensor field. So we'll also need later a spinor field. So here we can look for a generic transformation of this type. So we expect that there will be some matrix dependent on lambda, like some Dirac matrix acting on the field, acting on the spinor field here. So yeah, so this will be a Dirac spinor. And okay, so we can. So actually, yeah, to determine this, we can also see what would be the corresponding transformation for psi bar. So, okay, reminding that psi bar is psi dagger gamma 0. So then if we take the dagger of this, okay, we arrive at such an expression. And now, if we construct psi gamma mu psi, so this would be a vector quantity now. And according to this, it would transform in such a way. But then since it's a vector quantity, we know that it has that it should transform as a vector, so meaning that it should be transformed by just rotating the Lorentz index rho here. Yeah, with a lambda Lorentz transformation matrix. Yes. So here we are writing for simplicity for spinor which do not depend on the coordinates, since we already know how the coordinate would behave like this. And here, so this should be valid for basically any Dirac spinor. So then, okay, if we compare the two expressions we have, we see that, okay, so that's a kind of relation we have. And now if we postulate such a form for the matrix N of lambda here, so where lambda mu would be the same lambda mu as the one parameterizing the lambda here. But just now we have a new sigma mu for spinors here. We can just plug like this expression as well as this one here in this expression, and we can actually solve and we find so yeah, so we can play a bit with the Dirac algebra and so on, and eventually we arrive at such result. And okay, finally we find that the correct way is, I mean, is this. Okay, so then indeed, if we use this expression here and inside here, we get proper parameterization of the transformation on a spinor field in such a way. Yes, so that's how spinor field would behave under Lorentz boost or under Lorentz transformation. I mean, yeah, generic finite Lorentz transformation. Okay, yeah, so in case of an infinite transformation, then again, we will have the similar orbital type contribution here, and now this extra so-called spin contribution here. Okay, yeah, so that's what I was saying. So now we have this. So yeah, so now in general, for a field in an arbitrary representation R of the Lorentz group, we see that the field should transform in such a way so that there is a coordinate transformed as we have seen already many times, and then overall the field is okay multiplied by some matrix or at least one matrix for each index it may have, and in such a form where here this sigma mu will depend on the representation. So we saw the one for vectors and the one for Dirac spinor field as well. Okay. So okay, we discussed how fields are transformed under Poincare transformation, so either Lorentz transformation or translations, and both infinitesimal or finite transformations. So now just another reminder. So there is a Nutzer theorem which tells you that every time you have a continuous symmetry in a field theory, you can construct a conserved current. So this is well known, and then the conserved current associated with translational invariance is the energy momentum tensor TMU, which you probably well known is given in such a way here from the Nutzer theorem. And then there is a similar one associated with Lorentz transformations, so Lorentz invariance. So if your system is Lorentz invariance, then the following quantity, according to Nutzer theorem, should be a conserved current. So it's also related to the TMU here, and it has an extra piece. And actually, since here it was also associated with, so for each field there is a contribution here associated with how the field transforms. So here we recover this, we have the same sigma mu type of matrix, which represents the action of the Lorentz group on this particular field here. And here, when I say conserved current, it means that with respect to the first index here, we can take the derivative. Basically, that's zero divergence with respect to the first index here. So that's the statement of saying that mu and J rho mu are conserved. Okay. So, and the thing is that, so this is for generic classical field theory. And okay, in principle, if you have such a concept, a generic conserved current, you can define a charge by integrating this current, or I mean, by taking the. Okay, so yeah, so for example, if you think in terms of Cartesian coordinate and you want to describe the dynamics with respect to time coordinates, so x0, so that would be the what is called instant form of relativistic dynamics. So here you would like to define a charge associated with its current by taking this time component of the current, so that would be J0 in that case, and integrating over all space coordinates here. So okay, that gives you one definition for this charge. But then if instead you think in terms of transform dynamics of transform of the relativistic dynamics, here you want to describe evolution of a system along lifeline direction x plus. So now instead you need to take the plus component of the current and integrate over the other coordinates, which are now x minus and the transverse coordinates. So you see, for one conserved current, depending on how you think about the dynamics, you are led to define two different conserved charges. Charges, because okay, so now if the current is conserved, so you have so that's a zero divergence, then the charge you will construct will be conserved, but conserved in a different sense, because if you think about this one, that means that its derivative with respect to x0 would be 0, whereas if it's here, that would be the derivative with respect to x plus. I mean, anyway, that's the only coordinate that still depend on. Okay, and basically to see how such happens is quite simple. If you just take, for example, okay, let's say this guy. If you take the x plus derivative of this, that means that you apply it to the current here, and then if you use current conservation, so then you can say that this is equal to the term with mu not equal to plus, so that would be this, like opposite, sorry. And now you can argue that this is 0 just because it's these are total derivatives. So if you neglect boundary terms, and that we will do quite systematically, then then okay, so then that's 0, and that's a statement that conservation of the currents implies a conservation of the current charge in such a way, and that would work both for such kind of Light-Cone charge with respect to X plus evolution and this kind of Cartesian charge with respect to the X0 evolution here. But in principle, okay, these two are two different quantities. And so now, so that was for generic current, but now if we apply it to this T mu, so the conserved current associated with space-time translation, and this G rho mu nu, so the conserved current associated with Lorentz transformations. Now we can define conserved charges. So in the case of Cartesian coordinate or instant form, we take the 0, we take one index to be 0, like the first index to be 0, and we integrate over space, three dimensions of space. Whereas if we want like this front form of the dynamics, it's plus in terms of like evolution in X plus, then we will take the plus, I mean, like the first index to be plus, and we integrate over X minus and X stuff. And so this, again, that would be the, so in both cases, we would get the two objects, so this P mu here, and which would be the conserved charge associated with space-time translation, and here, so, and that would be the momentum, total momentum charge. And here the M mu nu, which would be associated with Lorentz transformations. So all this so far was basically at the classical level. So now, if we want to move to quantum field theory and discuss how these magnetic transformations happen. So here in quantum field theory, we would like to have transformation encoded by commutation relations, at least infinitesimal transformations. So for translation of some generic local operator here, okay, depend on X, we would like the action of infinitesimal transformation to be encoded in such a way at so linear accuracy in the small translation. So by this, so basically, okay, we would promote this, okay, such a charge like this P mu here to be an operator, and then the translation, infinitesimal translation will be obtained. Okay, like the effect will correspond to this commutator of this operator now, momentum operator with the local operator you consider. And similarly for the action of infinitesimal Lorentz transformation, you would have the same, but now with the mu operator, and that would be with the small lambda mu parameter. Okay, like parameterizing what Lorentz transformation you consider. And okay, so if you have this for infinitesimal transformation, then you can actually reconstruct what would be the effect of a finite transformation. So for the case of translation, that would be okay, that would be in such a way. So you would have the your local operator, which will be multiplied on both sides by exponential of this P mu. Okay, with opposite sign. And so now if you see that if you expand at small a mu, okay, basically at linear order you will recover this. So that's, well, consistent with each other. And in the case of Lorentz transformation, so the finite version of this would be this. So now, I mean, we knew that the transformation was okay, changing both the coordinate and multiplying by some matrix with the appropriate representation of the Lorentz group of the operator you consider. But we want to encode this by the mu, and so basically, so the action of mu in such a way should basically reconstruct this. So now we compare all the this expression with what we had before. So this, so for example, 19. So it could be. Yeah, so here, yeah, like infinitesimal translation was linear in A, like the effect of linear in A, and we're just giving the derivative with respect to the respect to x in the same direction it's mu. And now we would like to encode that by the commutator. So basically that means that that the commutator here should act as derivative along the mu direction on a generic local operator. And okay, similarly, if you compare this to the to the expression if you compare like the infinitesimal if you take the effect of the infinitesimal Lorentz transformation we had earlier, so it was expressed in terms of combination of its mu and derivative at on the field, and then extra rotation if needed, and now you want it to be encoded by the commutator here. So that will mean that this commutator here now is acting on, and mu is acting by its commutation in such a way. So it gives you the derivative with the proper coordinate here to have this kind of orbital piece of the Lorentz transformation, and here like the extra multiplication of any indices you may have in the considered operator here. So now actually, okay, so basically that's what we need. So basically, if we have indeed this these commutators which are realized, so that they act in such a way on any local operator, we can actually use the Jacobi identity of okay, which is generic for commutators, and play with this, and we can find that actually this. So if we okay, basically apply, for example, another P mu, and then use that, we will basically find that the P mu and P mu has to commute. And okay, then we have more complicated relation involving the generator and mu of Lorentz transformation, but okay, basically we get this, and this is what is called the Poincare algebra. And okay, so we have this in general. Okay, it's just that one remark here is that we need also that sigma mu r representing the Lorentz transformation for operator in the implementation R. That should obey also the same commutation relation as this, but now as matrices with respect to their extra indices here. Whereas here, these commutations are basically as quantum operator. So, yeah. So yeah, so here P mu, M mu, and this local operator are here like the commutation is commutation as quantum operators. Okay. So now that we have this Poincaré algebra. So this was general, it was not, so this is valid both for, both when considering evolution along the time-like direction is 0 or along the light-like direction is plus. But now we can have a look a bit at this and see what we get in both cases. So if you now first consider evolution like in this instant form of relativity dynamics, so meaning that we parameterize along the time-like direction 0. So now yeah, so in that case we have to differentiate between two types of transformations. So because now we really consider we want really to slice the whole space-time basically in terms of slice of constant x0. And so yeah, basically you have the system at some given x0, then you evolve, so that's a different slice and so on. And so then we have to differentiate between Poincaré transformation, which leaves which if you act, you stay in you keep the same, you don't change the slice of constant x0, and the one which change such thing. So if you consider a slice of like a fixed a surface of fixed x0, so given time, and then if you perform space translations or just the ordinary rotation, you will still have the same x0. I mean, so you don't change that. So this is what would be, so in that case, like space translation and space rotation would be what is called the kinematic transformations. So the kinetic part of the Poincaré algebra. So basically that would be transformation which really keeps this same yes, same x0 hypersurface. Whereas if you have if you consider, for example, time like translation in time, obviously you will go from a hypersurface of a given x0 to another one because you translate it. So by definition, you are not in you move away and you are not in the same hypersurface. Or if you perform arbitrary Lorentz boost, in that case, as you probably well know, if you perform Lorentz boost at the Cartesian coordinate, you have a mixing between the time and the transverse direction along the boost. And because of this, like if you perform a boost on a system, so basically you don't keep the same x0 hypersurface, but you kind of arrive at a different hypersurface where you have mixed with x0 and the time and the space coordinate. So basically now you see that in this instant form of the dynamics of the illusion form. Okay, we have really we have on the one hand like the space translation and space rotation, which are so-called kinematic transformation, and on the other hand you have the time translation and Lorentz boosts, which are the so-called dynamical transformation, and which can be considered as generalized Hamiltonian, because that's what will describe the evolution of the system. Because that will move from a surface of a given x0 to something else. So either another x0 or something more complicated. But yeah, so that will contain somehow information about the dynamics of the system. Whereas the other one, the kinematic one, we will not, because we are still at the same zero. So now, if you consider instead the front form of the relativity dynamics, so now we want to describe the evolution along x plus of the light evolution. So now we have to see which transformation affect or not the hypersurface of constant x plus and not x0 anymore. And now still we have translations along like the transverse direction, so x perp, or along x minus, which would keep this plus hyperplane fixed. So that would be so this would be kinematic transformations in that sense, kinematic generators. But now for if you think of Lorentz transformation, it's a bit more tricky to see. Okay, like one is just if you just make a rotation inside the transverse plane, obviously that will not change, that will not affect x plus, so that it still maintain the plus quite constant hyperplanes. So a rotation within the transverse plane, so along the long axis, if you want, will be kinematic as well. But it's just one rotation, not the others. And then it happens that there are still two others. Okay, which
No, it takes a while.
Okay.
Just yeah.
Okay. Yeah. So now you have this. You consider like transformation associated with this m plus I. We can find that they are as well kinematic, and this okay now in Light-Cone coordinate it's a bit since there is a plus here, it's actually okay a bit hard at first to see what it is, because it's kind of a particular combination of transverse Lorentz boosts and of rotations along a different axis than the longitudinal axis. So it's a bit mysterious at first, but then okay, we see that they are kinematic. So we have all this. So we have okay like 3 components of P, and then here there is only one because it's just M1, 2. And here there are 2 of them because I can be 1 or 2. So that's 6 kinematic generators so far. Which was okay, like in the instant form, there were 6 kinematic generators and 4 dynamical. So here we have 6 which are fully kinematic. Now, if we have P minus operators that would correspond to translation along X plus, so obviously this will change the X plus hyperplane, so this is dynamical. And then we have some other component, like now with the minus here, which are 2, so we have two such objects with n minus 1 and n minus 2, basically. So these are dynamical as well. And but then there is still a 10th generator here, which is m minus plus. And this one is actually a bit peculiar. So this is the one associated with longitudinal Lorentz boosts. And okay, think about what's going on when you perform a longitudinal Lorentz boost. In perform longitudinal Lorentz boost, that's the thing I was showing you at the very beginning. So you have the x plus, which is multiplied by this parameter here. You have the transverse coordinate, which is invariant, and then you have the x minus, which is again just multiplied, but okay with the inverse quantity as the plus. So and now, if you consider a plane of a hyperplane with some fixed x plus. In general, when you perform the Lorentz boost, it will be transformed into a hyperplane of this exponential omega times x plus. And so in general, that would not be the same. So in that sense, we can expect that this longitudinal Lorentz boost should be dynamical in general. So depend on the dynamics. But if you take the particular case where you take x plus equals 0 hyperplane, then you go from 0 to 0. So then that particular plane is not changed and stays the same. And so basically for the particular case of the x plus equals 0 hyperplane, then Lorentz boost become kinematic and are not encoding anymore the dynamics in this particular case. So in the insert form, we had 6 kinematic generators and 4 generators, 4 dynamical generators encoding the dynamics of the system. Whereas here we have, okay, depending if you are at, so either the same situation for generic x plus, but in terms of, but if you look at the particular hyperplane x plus equals 0, then you get one more kinematic generator and one less dynamical generator. So that's a simplification because the kinematic generator are simpler. So that's a little gain when we consider evolution along x plus rather than x0. So now, okay, let's consider like the kinematic generators. So okay, forget what Lorentz boosts for the moment, but like the other kinematic generator. So if we write down the like the corresponding component of the Quenching algebra, we have this expression. And interestingly, if we take all them and we add as well the P minus for the translation along x plus, as the generator for translation along x plus. So this one will have only one non-trivial commutation relation between with these guys, which will be such a way. And now, if you think about all this, actually, this is the same algebra as now the Galilean algebra in 2+1 dimensions. So basically, in a sense, looking at a relativistic system in 3+1 dimension, but in terms of this transform of the dynamics, so it's evolution along its plot, it's kind of I mean, you recover some kind of similar dynamics as what is the case for a non-relativistic Galilean system in 2+1 dimension this time. And okay, like here's the correspondence. So like the operator PJ for which corresponding to translation along the transverse direction. So that would be in the Galilean algebra like 2D momentum, so like this spatial momentum. Yeah. P minus here, that would be so here which plays a role of translation along x plus, so that's kind of like from Hamiltonian. So indeed in Galilean case that would be the ordinary energy, so that would be the Hamiltonian as well. Now the P plus operator would I mean just appear here actually as a only non-trivial appearance in the Galilean algebra here, and so that would correspond to effectively to a mass, but like I mean this P plus in the relativistic case would be analog to the mass in the Galilean 2+1 dimensional system. And now, okay, so yes, still the M12, so which was rotations within the transverse plane. Now, okay, that's really the angular momentum operator in the only that's the only angular momentum operator you have, because it's in the Galilean algebra that here you have two-dimensional space, so you have only one component of angular momentum, and so that would correspond to this guy here that we had. But now the interesting thing is that this particular combination of transverse Lorentz boost and rotations, which are a bit mysterious now, in this analogy, we see that this now corresponds to two-dimensional transverse Galilean boost. I mean, Galilean boost in these two dimensions, which now for us correspond to the transverse directions. So now we have an interpretation of this, and we understand a bit more what it is. So because of that, when we consider evolution in along X plus, it is convenient to not to talk about longitudinal and transverse Lorentz boost, for example, but still keep the longitudinal Lorentz boost, but instead play with transverse Galilean boost. I mean, like basically this thing, which should be simpler, instead of transverse Lorentz boost, which would be complicated in general. Yeah, and so yeah, and just a word about the M minus plus generator, so the generator of longitudinal Lorentz boost. So this one is not included in this Galilean transverse Galilean subalgebra of the Poincaré algebra here. So that's an extra one. But then we can see that it has a quite simple transformation. So basically, it acts on the others just by rescaling them according to the indices they have. So basically, for any upper plus index, we get rescaling. So we get basically enhancements by epsilon omega. So any transverse index, okay, is irrelevant here. I mean, okay, so now we understand these three. So here we have like transverse indices which are relevant. Here we have a plus index and a plus index. So these guys get multiplied by this epsilon omega. This one is also changed, but only transverse indices. And whereas these guys have one upper minus, and so that means that they are instead reduced, I mean, or rescaled by epsilon minus omega, so the inverse power. So basically, if we perform a boost with such large Lorentz boost with large omega, so we have the P plus, which is P plus and N plus I here, which are, so these generators are enhanced. These ones are staying the same, and this one with a upper minus index are getting reduced. So this is I mean, okay, so this is basically some statement about how Lorentz dilation and Lorentz contraction work in this Light-Cone coordinates, and at least for the, okay, so this is only for the longitudinal Lorentz boost, but yeah. Oh, sorry. Okay, and just a remark, okay, of course, if the indices are lower indices instead of upper indices, then it's reverse. I mean, like because upper plus index is the same as lower minus, and upper minus is the same as lower plus. So then you would have a similar rules here. And so actually, just because of this, that gives us some kind of notion of power counting with respect to longitudinal Lorentz boost. So if you have like in the middle of a calculation in such like if you use like phone quantization, you can count like basically the number of upper and lower plus or minus indices on different terms, and then you can check that they are homogeneous in this set, so that they will be transformed in the same way, and if it's not, then probably you can send it here somewhere. So that's just a remark that it's quite useful in practice for cross-checks. So okay, to that we had a discussion about how Poincaré transformations are appear and affect fields both in classical field theory and in quantum field theory at quantum level, I mean. And like the difference between the case of instant form of the dynamics, like with evolution along this zero time-like direction, or the front form with evolution along the x plus light-like direction. So now, okay, we should come to the main topic. So which is light form quantization. So here I will first talk about scalar field for simplicity, in order to not be distracted by all extra indices and so on, and see how it is performed and how it is different from other forms of quantization, typically which would typically use X0 as the evolution variable. So here, okay, let's first specify the theory I want to consider here. So here I just take a generic scalar theory in 4 dimensions. Okay, so I have Lagrangian with a term here, that term, and arbitrary potential here that I don't. I just keep it generic for the moment, and I will specify it later when needed. So here, if you write explicitly like the different values of mu, you can rewrite it in such a way that's okay. So this is still a classical case. So we'll have okay, one term with only the transverse derivative, and one term with one plus and one minus derivative. And with respect to x plus, like the conjugate momentum, okay, that would be take the derivative of this with respect to this derivative in x plus. So we repeat just this term here. Okay. And if we look at Euler-Lagrange equations here, we can that easily, and we get this equation of motion, right? So that's really basically a Klein-Gordon equation with some arbitrary potential. And here, okay, if we separate the contribution from the spatial derivative and move them to the other side, okay, we can write it in such a way here. Okay, this would be the classical equation of motion of this generic scalar theory. And okay, and already at this stage we can make a few remarks, because just already at this classical level there are some very important differences compared to when we consider the instant form of the dynamics, so along time-like direction x0. So first is that okay, this like now it's x plus which plays a role of time. So actually the equation of motion is only with the first order, like only a single derivative in x plus. So it's really a first order equation in x plus. So if you want, this is a parabolic equation. Whereas if you consider evolution along x0, here you would have double x0 derivative, so that would be second order in x0, and that would be a hyperbolic equation of motion. So that's quite. So these are quite different equations in general. I mean, quite different mathematical properties. And then the other thing is that here you see like this Hamiltonian conjugate density here with respect to the like for the evolution in x plus here, you get derivative of the field with respect to x minus. But then if you consider a hyperplane of constant x plus, and say, okay, someone give you what is the scalar field on this hypersurface, you can actually calculate this because you have like this hypersurface extend along the x minus direction. So you can calculate the derivative, and so you can calculate that. So it means that this guy is not independent of the field on this plus hypersurface. Whereas if you have if you look at evolution along its minus, its zero, sorry. Here, what you would get, you get a pi zero here, conjugate momentum, which would be derivative with respect to its zero. And so that's if you know only the field on a hypersurface of constant x zero, you cannot calculate the derivative with x zero because that would require going away from this hypersurface. So you would need extra information, which would be this pi zero on the hypersurface of constant x zero. So I mean, it means that okay, like the two require different initial data, and that's actually basically completely equivalent to saying that okay, in one case you have a parabolic system with only first order equation and like first order derivative, so it requires less initial data than the other case, which is a hyperbolic equation. So with second order derivative respect to x0, which will require more initial data. It requires on the hypersurface of constant x0, it will require both the field and the conjugate momentum pi zero, like the analog of this guy. So these two are completely equivalent statement, but I've already showed you that it's that already at the classical level, these are even though it's the same system, you know, that is just parameterized in a different way, and the equation, like the evolution, has a completely different mathematical properties already. So now, okay, we can also just since we are here, we can also write down the conserved current associated that we get from this Lagrangian density. So we can write down the T mu here, and okay, we get this like done with the derivative, and then the metric times the Lagrangian density. And so if you have this, then okay, you can look at calculate the different component of the conserved charge, like the conserved momentum here, like the charge, momentum conserved charge. So by integrating, as I already told you, along the x minus and x third direction, like the component here, where we take the plus as the first index here. So here, if you take plus plus, like the metric would be like G plus plus would be 0, so that term will drop, and for this guy as well. So for the first two, like the P plus and the PJ, we will do a contribution only for the first guy, and here the second term with the Lagrangian will completely drop. And remember that this Lagrangian here, that would be the only place where you have the arbitrary potential here. So which means that here this P plus and PJ are completely independent of the potential. So, and then on the interactions. And that's basically what I already told you, that these two guys at so they correspond to kinematic transformations. So translation along the x minus direction and translation along the transverse directions. And so this guy keeps its plus equal constant hypersurface the same, so they should not depend on the dynamics. So here you see it, like the potential completely drops from that. Whereas for the minus, G minus here, now we integrate this component, but now, okay, if we take G plus minus, that's 1. So then you will have the dependence of the potential. And actually, if you calculate it, in the Lagrangian, there was a term with the plus derivative here. But now there will be also a term with the derivative in plus and minus, and that would cancel each other, and eventually the T plus minus will be just this here. So this would be basically the classical Hamiltonian density, if you want, but it integrates to the P minus in terms of like in terms of evolution along X plus, yes. So now this guy depends on the potential here. So definitely this guy, which is associated with translation along X plus, knows about the dynamics. He has a potential here as it should. Now, okay, if you consider like the conserved current associated with Lorentz transformation, for scalar we have not this extra sigma mu term, but we have only the kind of orbital like term here. So we can just plug this expression we had. I mean, like we can calculate, and here we see that this two. So this guy, which the interpretation of transverse Galilean boost here, and this one, which was associated with rotation along the within the transverse plane, and we told that there were kinematic transformations. So indeed, we see that the potential drop for the same reason as earlier. Now we have the Lorentz boost, Longitudinal Lorentz boost. So in that case, it's funny because we say that this guy was in general dynamical. So depending on should depend on the interaction, except on the hyperplane x plus equals 0. And here you really see that because there is a first term which is independent of the potential, and then there is a term with x plus, so that would cancel that would vanish for x plus equals 0, and then with t plus minus. So this Hamiltonian density here which depend on the potential. So indeed, that's exactly what we discussed earlier, that this conserved charge associated with functional Lorentz boost is in general dynamical because of that, but except in the x plus equals 0 hypersurface. And then finally we have the last guy here, which is dynamical. Okay, so this is dynamical combination of rotations and boosts, and that guy, yes, okay, there is again appearance of this which depend on the potential. So this contain interaction. So indeed, this is a dynamical quantity. So okay, so that was so that's what we find on the capital level. So now, what about quantization of this system? So we have all this expression for all the conserved charges associated with Poincare transformations, and we have the equation of motion here. So basically, what does that mean, quantizing the series? So one way to think about it is just, okay, if you have this, you promote this, like the field and this conserved charges to operators, and then you have to specify all the commutation relations between them. And okay, they are all specified and that it's consistent. Okay, then okay, that's the quantum version of your theory. But then, what does that mean, consistent? Okay, we have some requirement. So first, this P mu and mu nu, since they are supposed to encode the Poincare transformation, so they should obey between them the Poincare algebra that we already showed earlier. So there are like some given commutation relation that they should obey. Okay, fine. And we already said that okay, when the commutation relation of this with the scalar field should be such that they generate okay, translations and Lorentz transformations. So basically they are fixed to have this form. So we already know all these I mean, all these commutation relations, all this and the Poincare algebra, that all this should satisfy. But we still don't know the one of the field with itself, essentially. That's the one which is missing here. And in particular here, we have the case of mu equal plus here. So this, and that, okay, we want this guy, since it's the one specifying that, like giving the evolution along x plus, we want this guy to somehow encode the equation of motion that we have here. And this, okay, like this equation of motion. So okay, there is a plus derivative of the field. Okay, there is also a minus, so we'll see what we do with that. But then, okay, and yeah, and we have also expressions that I showed you before for the at classical level for this classical P nu and N nu as a function of the classical field. So okay, let's say that let's require that the quantum version of this are the same expressions, except that we symmetrize the product of the field. So for example, for Pj, we have term with derivative in minus or in j, so we just symmetry that, so we have this particular order, so minus j or j minus and with a 1/2. So basically, okay, we want all this, but we still need to find what is okay. Basically, the problem is to find a commutation relation for the field between x and y. So at least that at equal x plus and y plus, which would be consistent with all this, and then that would provide a definition of the theory at quantum level, which would have all the Poincare transformation properly encoded in such a way, and the proper equation of motion that we have at the classical level already. So here there are several ways to do, like traditional ways to follow this Dirac-Bachmann method, which is very powerful, but very painful as well, because somehow this is really this method really is tailored for systems with second order equation of motion, like with two derivatives. But whereas here we have only one single derivative, as I already told you, it's like parabolic equation of motion. So because of that, then if you use Dirac-Bachmann, that will say that, oh yeah, we have so first step will be, instead of thinking of that as a parabolic equation of motion with single derivative, that would be a system with second order in derivative, but with constraints. And okay, then we have to deal with how we treat these constraints and all this. I mean, that's in principle, there is a well-defined method, but it's very painful and very long. And then actually, there are also another method which has been proposed more recently, which is really alternative method and which is really done for a system with first order equation of motion, and so that one we can apply, and it's much simpler. And so basically here we stay with this first order equation of motion. And as a system with first order equation of motion, it is not a constraint system actually. So we don't have to worry about constraints because there are none. Constraints here is just an artifact if we use this Dirac-Bachmann method, okay, which is unnecessary. So here we can completely bypass this. But here actually I will just show you even I mean something inspired by that method, but even simpler. It's just okay. We just want to see what this kind of hypothesis here about the representation of the Poincare transformation, kind of what hints they give about the commutator here. So here I will make one more assumption, which is that this commutator, so here is commutator of two operators, and I will assume that the result, so the commutator itself, is not an operator, but a C number, like a complex number values, like what is often the case for commutators, but not necessarily always for. Okay, so now if I take again like the expression I had for the P plus. So I have this, okay, this expression. So now I consider this to be the, so here it's already symmetric here. So if I can just like promote this guy to be the quantum version as the operator P plus and this to be the field, quantum field, the operator. So just keep the same expression otherwise. And if I just calculate the commutator of such object with the quantum field. So now that would be okay. Okay. So here is basically just integration over y minus and y perp. So I write it this way. Okay. And so here I just have the commutator of the integrand that was in P plus and with this field by x. So here I just use the standard properties of the commutator. So basically I would have commutator with this guy or commutator with this guy. And since here I assume this is a number, so I don't care about the ordering of the commutator with the left property. So I just have two terms which will be equal, and okay, so I get factor 2. So okay, that's what I have. And I can do the same for the Pj. And okay, I would have something like this. So here I would have either commutator with that guy or with that guy, and so on. So I have term with a minus derivative here or j. And then here again, I do integration by part along y minus or yj here in order to rewrite both terms in the same way here. And now if you look at this equation here, so for Pj, so here I have commutator with a minus derivative of the field and the field. And here outside we have derivative in j for Pj. For the plus here, we have something similar with a minus, again, like same commutator here exactly. And the difference is that now I have a derivative in respect to y minus here. And if these two equations, I want them to be equivalent to that, it means that this commutator, like to some factor minus I here, it should give you the derivative. So basically, what I need is the result of all this to just pick me this at point x. And basically here, that guy at point x equal 1. So yeah, basically that would be this relation here that I need. And here, like the way is just that if this guy is proportional to just delta along minus and perp coordinates, that will kill completely this integration and replace by the y. I also need a 1/2 to cancel the 2 which was here and in the previous expression, so I have 1/2. And okay, if you are careful with the i's and the minus and so on, okay, here you see that there needs to be a I. So just by looking at how okay, I try to formulate properly the transverse translation and translation along x minus, I see that there is one particular expression for the commutator which gives me what I want. So okay, let's take this as a candidate commutator. And now okay, so this is not exactly what we wanted because we want the commutator for the field was its derivative, so we need to take so now that remember that was commutation relation at like kind of analog of equal time, but now that's x plus equal y plus. But then the y minus has nothing to do with y plus in principle, so we can really integrate that by staying within this x plus equal y plus. So okay, we can integrate and we get okay, we integrate the delta into a Heaviside theta function and we get a constant here. So, okay, that's one expression, but we need to fix the constant. But then, okay, this commutator, I mean, by definition, this has to be anti-symmetric. So if you impose anti-symmetry, that actually would determine completely the constant here. So here, this guy, you can, okay, I mean, you can basically anti-symmetrize this, and you would get this expression. So now this epsilon is basically the anti-symmetrization of this. So this, okay, or if you want, that's a sign function. So that this would give the sign of x minus minus y minus, so the difference of the theta functions. So, okay, so far we have now this candidate expression for the commutator. Okay, which is associated with, okay, it corresponds to that one as well. But now, okay, we checked only the effect on like the commutation relation with P plus and Pj. So now if we plug this expression or equivalently this one for the commutator of the other kinematic generator again, yeah, okay, that works, and we get by just inputting this commutator, we get the expression we want for the other kinematic generators. So basically, which means that all these kinematic transformations are properly encoded in the classical theory. Okay, in the case we take this commutator. But of course, that was only kinematic transformation. Now we need to understand what's going on with the dynamics. Okay, first, there was this particular case of longitudinal Lorentz boost, which is kind of a hybrid between kinematic and dynamic. So here, if we calculate again the commutator using this same commutator here for the field, we arrive at such an expression. So, and indeed, that's what we want. So, provided the P minus is properly represented, so that will be related to a derivative in X plus acting on the field, then that's exactly the expression we need. So, okay, so basically this one works if the commutator P minus and phi work as well. So now, okay, now we have to really look at the dynamics and look at this guy. So now the density associated with P minus was this T plus minus of X or Y in this case. So where there was a transverse derivative and the potential. So here, okay, we can at least formally calculate this commutator here, and so here we will pick one field out of that, and okay, get this commutator, and then if it's for this, we will integrate by part the derivative to get this, and here we have take the derivative with respect to the potential, so the prime, so the derivative, in order to extract one part of the field, and so it's the one that we can commutator with. So in general, we have this expression here. So now, if we take if we multiply by I, that is what is supposed to be related to derivative of the field with respect to X plus. And then if in addition we also take derivative with respect to X minus, now the derivative with respect to X minus will act only on the field here. So we will recover this. And this, okay, it was a simple commutation relation which give only delta function on minus and third direction. So basically we get rid of this integral and we get this, and this, if we ask, okay, like this really reproduce the classical equation of motion we had, but now with field converted to classical to quantum field operator, and provided that that we have this identification that derivative with respect to the field is encoded by commutation relation with this P minus C. So yeah, we get this. So with this identification, we get this quantum version of the equation of motion. So that's exactly what we want. But again, here it was with a minus derivative. So okay, just let's look at what happens if we don't use oh yeah, I'm almost done. If we don't put its minus derivative instead, we would have we can plug here the expression we had for the commutator, which has this sign function. So that would be here. And basically, this would be a non-local equation of motion now. And it is often noted in such a way, but okay, you have to think of like the proper definition of this inverse derivative here. It's really like convolution with this sign function here. So in that sense, yes, that's a compact way to write this non-local equation. And now using the same thing, okay, you can also finally calculate the same like at the final commutator, like with this over dynamical generator here. And then we get like by just putting the commutator and so on, we get such an expression here, where here we have this non-local term. And here you recognize what we have here, so we can just replace here. And that's this, and that is indeed what this should obey. So that's really the thing we wanted here. Okay, so basically this is such a form here. So now, okay, what's the conclusion is that if we take this commutator here for the field, then we get all the proper commutator of the field with all the Lorentz generators. So which means that Lorentz transformation are correctly encoded, and we get the quantum version of the equation of motion. So okay, we are still at the same system with the same dynamics, but at the quantum level. And okay, if you are brave and patient enough, you can go on and try to check that you have actually the full Poincare algebra, which is indeed recovered. So if you calculate the conditional relation between the P nu and N nu, we recover the expression. But okay, so that's okay. So that's long and painful, but okay, that's what we get. So in that sense, we see that was a simpler way to construct the theory at a quantum level, and the bottom line is that okay, so this is the commutation relation we need for the field, and okay, so that's it. And okay, so we'll continue with the following further study of this scalar series that we also physics of the quantization structure. Yeah.
There are questions? Also in the Zoom. Okay, if not, John is here for this week and the next one.
Yes.
So just feel free to contact him for questions. Okay, he will be around. He's in the room, Lena's room, so very close to mine. Oh, there is something in the chat.
Oh. Okay. So yeah, I mean, like the lecture note is already in principle, it's already uploaded on the website of the Indico, yes. So yeah, I mean, it's already there in principle, yes.
Anything else? Okay, if not, thank you very much to everybody.
But this passage is only message charges. Go straight to this. But there was the minus sign here in both.